So I'm talking about the bond energy, and then they show this organic chemistry formula. And they actually purposely write this one this way so that you have a knowledge is that what are the connectivity of here. You have a double bond, the carbon, and the CH, there are 4 CH bonds. And then there's a 1 HH bond. So for me, 4 CH bond, and 1 CC bond, 1 hydrogen bond. And it takes energy to break those bonds, and I know what is the bond energy for doing those. And if somebody write this way, and then that means actually carbon and carbons are connected, and those CH3 means there are 3 CH bonds. This is what you guys just learned from the portion of the organic chemistry here. So in this case I have nothing but, I guess, 1, 2, 3, 4, 5, 6 CH bond, then 1 CC. So this is what's happening. And then what are you going to think about is, this is a hypothetical state. Okay? A hypothetical state is everything is falling apart. Okay? So there are hydrogens everywhere, carbons everywhere. I'm just saying the atomic state, atomic gas. So this is what I'm thinking about in my head now. So what's the bond energy is there? You need to break 4 bonds. You need to break 1 double bond, 1 single bond of hydrogen. You make a soup of these atoms. That's not happening, but thermodynamics is actually very convenient for me to calculate that, because what I need is a difference between this state and difference between this state. And if I combine that, actually, I can predict the delta H reaction. And for these atoms, make a new, I guess, partners, new connections, and the carbon has 1 bond, and the rest of them are CH bond, and there's 6 of them, and this is an energy that I can get. So then I need to look at the bond energies, and the CH bond is 414 kilojoule per mole. And the CC double bond is 611 kilojoule per mole. And the hydrogen is 436 kilojoule per mole. Okay, and I guess this is the same thing here, 414 kilojoule per mole. And the CC is 347 kilojoule per mole. So you can look at those, this is a bond energy, you can find it there. But now you need to take a pause and think about it, what that really means. Energy state-wise, let's say this is your compound, and this is your compound, and I don't want to bias which energy is higher, so I will just put it in the same way. And you're thinking about bond energy means became atomic gas, the energies that go up, and they're essentially going down here. Okay. When you break those, they became very unstable. The energy state goes up, and using that, then they actually combine, the energy states are coming down. So for this, to make these stages, these energies are needed, right? And to make these stages, these energies are essentially liberated, right? They are kind of given out to the system, so they will have a different sign. So the bond energy itself is given as a positive number, and because energy needed to break. Right? So if that then makes sense to you, then this is what it is. So this is an energy, and energy on the constant pressure, we call this is an enthalpy. We can say that. So this first process is essentially 4 times 414, 1 times 611, 1 times 436. So this is a positive number. And because your energy is going up, and then you can think about this is a plus, this is a negative number, which is the other side, which is upon forming this bond, this energy will be liberated because this high energy atomic cloud will give a rise to this stable compound, and so those energy will be liberated. So now this is 6 times 414, 1 times 347. And that is your heat or delta H of the reaction. I think that's what this is about. Yeah. Okay. So the top portion is 2703, 2831. So therefore the overall is minus 128 kilojoule. Okay. So what happening was this energy of this before and after is lower, and is lower by 128 kilojoule. So what that means is in the before they have a higher energy state and go even artificially convenient. This is a very thoughtfully convenient way of looking at let's break everything, right? This has an enormous energy, but that energy will be a nice reference state for me to estimate what is the energy state between this artificial, let's say this is a state, and we have an understanding about how much energy is needed, how much energy will be liberated, so that we can calculate the net energy, the difference between this break the bond and forming the bond. Okay? So bond energy, not only the itself is meaning that energy needed to break it, but the negative sign of the bond energy is energy generated upon formation of the bond. And so you can use those as both ways. It's not as bad as I thought to finish this one in time.